Hello and welcome to the presentation Jailbreaking the Apple HomePod. I am very excited to be the only true speaker at this amazing conference. Now, welcome the humans on the stage and enjoy.
All right, hello. Thanks for the introduction, Siri. So let's go. Can you hear me? Yeah, perfect. So our target today is the Apple HomePod. So the HomePod is Apple's smart speaker, which is similar to Amazon Alexa. It is used for music and smart home controlling. It was released in October 2020 and runs a custom version of iOS, kinda. Well, it's all kind of the same, but officially it's like tvOS for whatever reason. It has an A8 CPU, which is pretty much the same as the iPhone 6, and it is vulnerable to the BootROM exploit Checkm8. So there was previous work on the HomePod. So I guess the first to tweet it out was Chris at Corellium, which they virtualized the OS. So it does not really count as a jailbreak because it's running on a VM and not on a real hardware, though this is kind of the first instance of this OS getting like, I don't know, SSH or whatever. There was also previous work on Ingo. So this guy figured out there's a hidden connector at the bottom of the HomePod, and he reversed the pins. And he also figured out, okay, we can do UART, we can do USB, which is pretty cool. And he designed a custom PCB and also published it on GitHub. So you could get the files and get yourself one of the PCBs. You got to order that and solder that. So there was also Checkm8 running on PongOS, SSH working. This is all before we started, so we were wondering, okay, so what exactly is left to do? So the current status is that the HomePod jailbreak never really became a thing, right? Official Checkm8 stopped working around iOS 15. I'm not quite sure whether that changed, but I think it did not. So it does not, to my knowledge, support iOS 15 or 16. Development kind of stopped and the approach hit a roadblock. Also, HomePod USB is not easy plug and play. You definitely need a custom adapter. So yeah, let's see, what does it take to actually jailbreak the HomePod? Well, let's start with the hardware. How do we access the thing? So first you want to do is you flip the HomePod upside down. You use a fan or some kind of heat, hot air, and a screwdriver, and you can heat it up and then remove the plastic cover and expose the hidden port. If you do a really shitty job like me, it will look like that. But it's possible to do it without actually damaging it. Just be more patient. To connect to USB, Ingo published the connector on GitHub, but I could not figure out how to make one. I'm not really that hardware person, so I didn't know what to do with these files or how to order one. So I decided to instead make my own cheap 3D printable connector. These are the previous failed 20 attempts and revisions, but at some point I kind of figured it out, and this is the final printable 3D connector. So basically you print a little plastic, you put in a few pogo pins, you solder wires to these pogo pins, and you can screw it on and then connect to USB. By the way, I have quite a few pre-printed and I think couple assembled. So if you have a HomePod and you're interested, please take them because I don't plan to bring them back, so you can have it after the talk. Yeah, printable plastic piece, pogo pins. You need 4 pins for USB, 2 more pins if you also want UART. Though here UART is 1.8 volt, not 3.3, so you need to have an appropriate UART adapter. A couple screws, wires, hot glues, some basic soldering skills, And if you spend like $30, you can build like up to 25 adapters.
You know, the thing is, you can actually also build a proper connector, which we saw before, and it's actually quite easy. You take the Gerber files from the GitHub repository and you send them to a PCB manufacturer like JLC PCB. You just upload the files. And it costs around €1 for both PCBs if you buy them in bulk. And then there's about €15 or so in parts per PCB. And the advantage of this is that you have a way more stable connection. So yeah, I mean, it's possible to make it properly.
Yeah, well, for me, the 3D printed version was good enough, and I could get it faster. So, what's the take on the software side? This one, since you're not using it. Okay. So I will talk about a little bit about the boot flow. So the normal iOS boot, the BootROM loads iBoot from NAND, it verifies the image, and then it jumps to that image. So iBoot loads the kernel and the device tree and other components from the NAND, from the file system, verifies it, and then jumps into the kernel. Okay, so far so good. How do previous BootROM exploits work? So you enter DFU mode, and then you exploit with LimeRame or Shatter or StakeSauce, and then you inject the shellcode. And that shellcode lets you load an image over USB without calling the signature verification function. So DFU, inject code, and then you kind of talk with the payload that you injected, and you don't really do all the normal stuff. You just call into original BootROM functions and then manually call the thing from the payload and then boot it. So Checkm8. Checkm8 is a bit different. Checkm8 implements the Checkm8 BootROM exploit by first you go into DFU, then you exploit with Checkm8 and inject the shellcode. Then what Checkm8 actually does, they remap a BootROM page into SRAM, and then by fixing up the page tables, you basically have it in SRAM, and then since it's in SRAM and not DROM anymore, you can actually patch the remap copy. And then what they do is then they fix up some state, which lets you kind of be like, okay, this is not a DFU boot, but this is actually normal boot, and they kind of continue the boot as if it was a normal boot. So what happens is they load iBoot from NAND and verify it. They patch the patched BootROM page redirects the flow to the shellcode as soon as the iBoot was loaded and verified. The shellcode then patches iBoot after it was verified by the BootROM, and then the patched iBoot get executed, and you keep you warm your way up. There's a couple notes on Checkm8 on the implementation. So Checkm8 never actually patches the code signature checks, which is not really needed because you patch the bootloader files after you already verified it, right? The shellcode, patches the new iBoot after verification. So it's kind of cool since you warm yourself up, but there is a problem with the approach. So if you have a device which for some reason has a broken iBoot, either a battery store or something didn't work, and the device itself doesn't boot, in that case, Checkm8 kind of breaks because it relies on a valid iBoot. But if the iBoot which is installed on the flash is corrupt, then you can't also use this method to get like the code execution. So this is kind of the drawback of doing it that way. Also, Checkm8 on the boot iBoot, they patch iBoot to fall back into so-called soft DFU mode. So the higher level bootloader pretends the kind of more basic DFU USB environment, and they use that to upload a bigger payload because in the initial BootROM only SRAM is available and no DRAM, and SRAM is fairly small and there's not enough room to upload a huge payload. And then they just have the same injection procedure as in BootROM, and since all the checks are already patched, they're just good to go. Yeah, BootROM, soft DFU, patch. So when they upload the more stuff, they upload PongOS, which is a little kernel they built, and that patches the real kernel and then injects a custom Ramdisk, and then they continue to boot the Ramdisk. So they redirect it from normal to the custom Ramdisk boot. So what the Ramdisk then does, it mounts the real root FS on top of the Ramdisk with the union mount. It replaces a real existing daemon by mounting over user libexec, and then continues system boot. And then at some point, the system will try to launch that daemon, which is then their code, and then it waits for the user to unlock the device, and then the computer can upload more payload, a bootstrap, and then enable SSH. So in iOS 14, SAP adds mitigation to block jailbreaks. SAP detects a DFU boot and disables the file system encryption keys, which means you can no longer decrypt your file system, and when you try to boot, the device will just panic because it can't boot without decrypting the user file system. So what PongOS did, they exploit a ZapROM exploit in A10, and they just patch that check in the SAP. On A11, the workaround is on iOS 14.15, disable the passcode. Then the keys do not rely on that key, and you can still decrypt the user partition. And on iOS 16, they did even more mitigation. Basically, if you do a fresh restore and never ever set a passcode, it is fine. But as soon as you set the passcode even once, and then remove it later, it still doesn't let you boot because you still can't unlock the file system. So this is a great way to protect the user data despite having BootROM code execution. It's not really applicable to A9 and earlier, since they can't add the mitigation there. So there you can just still let SAP decrypt the file system. And this is not relevant for the HomePod because HomePod is A8, so it's even earlier. So we don't have to worry about any of that. Checkm8 has a couple problems with iOS 15. So basically there is the signed system volume, which prevents root file system modification. So we used to just remount the file system and then put our bootstrap, our SSH on it, and then have it. And then when we reboot and re-jailbreak, it's still there. But here, since the volume is signed, we can rename the snapshot, but then the device will never boot without like exploiting it. And we kind of want to avoid that, because imagine if you have your phone and it's jailbroken, you're on the go, and then for some reason it reboots and you just can't use it without computer, which would kind of suck. So this is kind of a political problem, because there's a solution to that, which is a rootless bootstrap. So we, instead of putting it onto the root file system, we just put everything in a different directory so it doesn't break normal boot. I personally am not a fan of that. So, and yeah, there's different opinion on that. A technical problem is that union mounts were removed for the kernel. So there's like a bit tricky on how to get the initial code execution into user space and continue there. And another technical problem is that iBoot removes soft DFU. So in BootROM, we can boot a patched iBoot, but in BootROM, we don't have enough memory to inject a big payload to patch the kernel later. And then it's tricky from iBoot to inject more code. So this is also a technical problem. I'm sure it can be solved. It just came up, and I think this is one of the reasons why the development kind of halted with Checkm8. A funny thing, this is actually, for some reason, a HomePod feature, which still exists in tvOS 16 and 17. It's not really used on the iPhone, but in the HomePod it is used. And we will come back to that later. But let's talk about how do we put the HomePod in DFU. And weirdly enough, you flip it upside down, remove the cover, you connect USB to it, and you power it on, and that's it. So it detects being upside down, and when both is true, it being upside down and connected to USB, it goes into DFU mode. It's pretty cool. The way it works is that the BootROM boots, and then it loads iBoot from the NAND, and then iBoot boots, and then iBoot detects that HomePod is upside down and USB is connected, and then iBoot makes it reboot back to the BootROM to DFU. So there's kind of a bit of a problem there, because what we do is we send patched iBoot over USB to BootROM, but that iBoot will not enter in recovery mode, is what we want to continue to boot, but will again drop back to soft DFU mode if the HomePod is still upside down. So there's two ways to fix it. Either after you exploited the BootROM, before continuing booting, you put the HomePod back on the side or proper way, or you patch iBoot to just not do that, and that's what we do. So I want to talk about my tool RainSnow. RainSnow is a tool for tethered booting. So it relies on the classic pond DFU mode, which we knew from like the LimeRain area. So basically what you want to have is like a stock DFU environment, which behaves like stock DFU, but just with the signature checks disabled. So you can just give it a normal unsigned image, and then it will be booted. And it performs LimeRain style tethered boot, which is we disable the signature checks and then already send every component patched, similar to a restore boot where we send all the components and like do iTunes restore. But here we just have everything patched and then do our own code thing. We don't rely on anything on NAND. So even if you remove the NAND or something on the NAND is completely broken, you can still boot at least into Ramdisk and then do whatever you want to do. And also an advantage is that you can boot any iBoot Ramdisk kernel regardless of what is actually installed. There's a little caveat because we can't actually boot any SAP. So we need to have a valid SAP there if we want to like do a normal boot and you mount the user partition. And then the problem is that the SAP only works with certain kernels. So if the kernel is too new or too old, it doesn't work. So if you want to do the complete boot, you want to have a kernel which works with that SAP where you have like a valid signature for. How do you actually disable BootROM SIG? How do you actually do BootROM SIG patches? Well, the first step is you take the public iPwn-DFU exploit, but that unfortunately corrupts the heap in the BootROM, and then there is like some heap checks before jumping there, and also it doesn't work. So Linus published a modified version of it to not corrupt the heap, so we can just take iPwn-DFU public, and then that doesn't break stuff. So what I do then is we modify the page tables. I make a second level page table, and then I remap one page from the ROM into the SRAM, and we fix that up by the page tables. So the page in the SRAM then we can patch and disable the signature checks. And the approach needs one unused page for the one you're going to remap from ROM to SRAM, and then one partially unused page where we put in the page tables. And since only a few entries are used, it doesn't really matter what else is on the page. So usually just take some stack page, because then the garbage on the top doesn't really interfere with the mappings at the lower addresses. So how does that work? Okay, let's enter DFU mode. We exploit Checkm8, and iPwn-DFU exposes read, write, and execute primitives over USB. We remap the BootROM page into the SRAM. We patch the remapped copy, and then we can just regular send iBoot over USB and boot iBoot. Since signature checks are disabled, we just use everything else from the regular flow. So the RainSnow boot disables signature checks in BootROM, sends a patched iBoot, and that can load the patched Ramdisk, custom device tree, patched kernel. All are pre-patched on the computer. The component patching is performed offline on the PC, so it's very easy to debug the patch finder for every single version without having to have an actual physical device with that version installed. You can enable and disable built-in patches from the command line. For example, if you want to disable signature checks in the kernel, there's just a command line flag for that. If you don't want that, just don't pass the command line flag. You can also specify custom patches from the command line. You just give it an address, the component you want to patch, like the kernel or iBoot. You give it an address, and then you just supply the hex bytes, and it will just patch it for you on the fly. So if you try to debug and test something, perform quick kernel patches, you just add the command line parameter, boot the device, and it patches the thing you want to do without having to export the binary in IDA, then converting it to correct format, and then sending it over and so on. Everything is done automatically, and it's very useful for research and debugging. There's actually yet another way to do custom unsigned boot from the BootROM. So instead of remapping the BootROM or applying code signature patches, you can send an unsigned image over USB and then manually call BootROM functions to prepare the image, skip the signature checks because the image needs to be unwrapped and put in the right location. And then you can redirect execution flow to the image manually by using the exec primitive calls, or for example, patching the ARM interrupt table, and that way you can also jump into the image. It's a bit hacky, but I guess it's one way of doing that. So let's talk a bit about the Ramdisk. So the first user space process which the kernel starts is /aspen/launchd. All libraries, all binaries on iOS, macOS, and so on have to be dynamically linked. There's no such thing as a fully static library. So at least you need to link against user libsystem b.dilib. And what actually happens if you run a binary is the dynamic linker is the first piece of code to actually run, which is at user lib dyld. So let's make a plan, okay? So we're making a custom Ramdisk. We have a stage 1, which is user lib dyld, which uses pure C, no external anything, which use inline assembly and syscalls to interact with the outer system, and we don't have any dependencies on that. We do stage 2, which is a shared library, which we will inject into the relaunchd later. And we have stage 3, which is Aspen launchd, which is our custom daemon. So the kernel launches launchd, but what really happens is that our custom linker runs first. So here you can see, I don't actually have to read it right now, it's just for the slides later. We use a custom inline assembly for syscall, then we wrap the syscall function to expose, I don't know, like sleep, stat, mkdir, chroot, mount, and so on. We allocate heap memory using the mmap syscall. We read stage 2 and 3 into the memory buffer from the Ramdisk. Then we mount the real root fs on top of the Ramdisk on /, which is a regular mount, which is not a union mount, so it hides all the files below, but we don't really need them anymore. And since it's writable, we can then, from the memory, write stage 2 and 3 just back on the real file system. We write stage 2 to /jb.dilib and stage 3 to jb-init. Next, what we do is we set the environment variable dyld insert libraries, and then we execute execv into the real launch daemon. And what that does is that the real linker runs, and the real linker injects our stage 2 library into the real launchd process, and then we continue our code execution in there. So what do we do then? It used to be that there's like launchd plists for all the daemons on the system installed, and they're no longer actually loaded from the file system, but instead they're like compiled into the shared cache and then get loaded as an xpcdict. So by hooking a C function in there, we can just inject our custom plist into the memory directly, and then launchd is like, oh, this is a daemon I want to start, and then starts stage 3 for us, and then that gets loaded as a daemon. So what stage 3 does is it opens up a TCP socket, and it expects it over to send a statically linked tar binary, except for the /system, but yeah, it doesn't have any dependencies which are not already there. And then we also send a bootstrap.tar, and then we just run the binary, the statically linked tar binary, and extract the bootstrap tar to SSH, and then make also stage 3 start SSH, and then we're good. Where do you actually get the bootstrap? So the OS doesn't have like any shell any bin, bash, ls, nothing. So you need to bring all of it yourself. There's an open source, easy to use build system for various projects for iOS, tvOS, and so on. Though I really recommend using my Ramdisk branch, which has a Docker container, so it will actually work on your system if you use that container. And then what you want to do is you pass in the SDK that you want to use, and then you can compile a bunch of projects. There's custom make files, so you have like bash, SSH, and so on. And yeah, that's what we use to compile the bootstrap. iOS mounts, on regular boot, iOS mounts a snapshot and not the real root file system. But we mount the real root file system writable, and that on its own does not destroy the APFS snapshot. Previously, jailbreaks would rename the snapshot, so the system can no longer find the snapshot and just had to fall back to mounting a real file system. But that no longer works on the current version, because now if the device doesn't find the snapshot, it will panic. So the trick is, normal boots will work fine, since on the next boot, the snapshot is mounted instead of the real file system. And since we didn't modify the snapshot, everything is still valid. A drawback on that is that the system will also restore the snapshot, so all our changes are lost. So what you can do is either not boot without exploiting, or But this is kind of also an advantage, because not breaking the seal serves as an anti-brick protection. So if you mess up the file system, and then you can't restore the HomePod because it doesn't have the IPSWs. If you break it, then you need to go to Apple and be like, the update went wrong, please fix it for me. But with this method, you'll be like, okay, I just do a regular boot and it will automatically remove everything. So it's kind of an advantage. And it's like stealth, like even mate attack malware is gone in the next reboot, and then can't run code on the next reboot anyway, so why keep it around? It actually, if you want to prevent accidental wipe, you can set auto boot to false, so it will not boot automatically, so we'll have to boot it manually. But this is easy to unset. Like, just connect it back to computer and set the variable to true if you change your mind and just want it auto boot and remove everything. But this prevents you from accidental boot, so then you just connect to PC and exploit it every time. If you really need, you can manually map the snapshot and break non-jailbreak boots, though I would not recommend that. PaleRain is another Checkm8-based jailbreak, which recently got some attention. It uses a modified version of the jailbreak unit that I presented, and it uses Pongo OS for the kernel patches. All right.
Okay, next up, tweak injection. So the thing is, now that we have a jailbroken HomePod, what should we actually do with it? And normally, what you want to do is load tweaks. What that means is, like, a tweak is a small library that you can load into your processes that are running on the system, and you can use them to change the behavior of iOS, or in our case, of tvOS, of the HomePod. How does that work? Normally, you take a tweak injection library. In our case, we use libhooker for that. And this tweak injection library will automatically load tweaks into each process. The problem, however, here is, in order to load tweaks, we need to inject the tweak injection library into processes. But in order to load custom code into processes, we need a tweak injection library. So it's a chicken and egg problem, basically. However, what we can do is, because we already have code execution in launchd, and launchd is the parent of essentially every process, we can just patch launchd. And what we do is we patch the POSIX spawn function, which is used to start other processes on the system. And to the environment variables, we add the DYID insert libraries. And we just make every spawn automatically add this environment variable, and when the new process launches, DYID will see it and load the tweak injection library for us. And yeah, we can do that simply because, like, on normal Unix systems, you usually do fork and exec. Fortunately, this is not done on iOS and tvOS. It just uses POSIX spawn, so patching POSIX spawn is all you have to do. And in our case, we load a library called JB-injector into each process, and this library will load tweak-inject, which is a library from the Puka to load all the tweaks and stuff. And JB-injector also does some stuff like patching POSIX spawn in every other process that is launched to make sure that when a process launches another process, that this newly launched process will also have tweak injection in it. Now, what tweak injection then does is, like I said, it's a libhookah helper library, and it loads libhookah, which provides all the APIs that you need for tweak injection, like function hooking, Objective-C method hooking, stuff like that. And it discovers which tweaks you have installed and then checks if it should be run, if it should be loaded into the current process. And in that case, we just load it. Now that we actually have tweak injection, the question is, what cool stuff can you do with a jailbroken HomePod? And the first thing you can do is, even without tweak injection, you can at least do some file system modifications. So simple things you can do is replace sounds on the file system. And yeah, for example, you can replace the timer done sounds. So if we do something like this, hey Siri, set a timer for 2 seconds.
2 seconds, starting now.
Hey Siri, stop. So this is one of the easier examples. Yeah. What we can also do is, like, the thing is, if you have a HomePod but you do not have an iPhone, then you actually have a problem. How do you even play music on it? Like, you cannot do that from Android because you cannot stream music to the HomePod via Bluetooth. But the thing you can do is you can install Spotify D on it. Spotify D is a daemon that Spotify provides. It's open source and can be used to stream music to other devices, and in our case, to a HomePod. And we can actually show that right now.
So the only Android device I own is my Nintendo Switch. Oh shit, we need to run it first.
First need to run Spotify D. Otherwise it won't work.
So I made a track and recorded it and put on Spotify just for this demo. So this is my track. Alright, just speaker first. I don't know how to use Android.
Yeah, the touch screen is really bad. Like, it's super annoying. Come on.
Try.
Yeah, I'll let you try. Yeah, so we're having a lot of trouble with the Wi-Fi, and so that's why it currently does not want to work.
I'll try. I think you can prepare that.
Okay.
Maybe show the backup demo.
Right.
Okay, got it.
Die Erde ist am Leben, 2020 ist das Jahr.
So, playing music from Android on the HomePod through Spotify.
Next up, we have another interesting demo, and I will just start with the demo first. And in this case, we need the camera again, because you want to be able to actually see it. We hope you get the reference. Hey Siri, close the door.
Closing the main entrance door.
If you want to open it again, hey Siri, open the door.
I am sorry, Dave. I'm afraid I can't do that.
So essentially what we did here is on the HomePod, there's a process called Assistant D, which is responsible for Siri. And then we also have Soundboard, which is the Springboard equivalent for the HomePod. And Assistant D, yeah, like I said, is responsible for Siri, and we just load a tweak into Assistant D. And we also load a tweak into Soundboard, and then we listen for specific phrases in all Siri requests. And if the keyword is detected, in our case it's door and open/close, then we just replace the reply and also tell Soundboard to show the red LEDs. And we just show the red LEDs by writing a flag to the file system and checking for this flag. So now that we did this, next up we have Siri GPT. Yeah. Now the thing is with Siri, you know it's kind of limited. Like you ask it something and you get this typical, I found this on the web stuff, and just tells you a really useless answer. So our idea was to hook up Siri to ChatGPT in order to get more useful answers. And what we did is we created a tweak that just intercepts all Siri requests. We extract the text and then use the OpenAI API to get an answer from ChatGPT. And what we then do is we just inject the text reply that contains the answer from ChatGPT. And I would just need to really quick install it. Okay. Let's do something like, hey Siri, what does the fox say?
Wap-ha-pa-pa-pa-pa-pow.
Damn it.
There was actually original Siri, so technical difficulties.
What should have happened? Hey Siri, how are you?
I'm happy to be here.
Was it a regular answer or a ChatGPT answer? I'm not. You think it was a regular one? Then let me just do it like this. Yeah, just reinstall it on there a couple of times to make sure it actually gets installed. Okay. Hey Siri, how are you?
On it. Hello, Linus. I'm just a computer programmer, so I don't really have feelings. Thanks for asking. How can I assist you today?
Hey Siri, what's the hook of the song When There Are No Strangers to Love?
Hello again. Linus, how can I assist you today?
Yeah, it's sometimes a bit broken.
Hey Siri, what's the hook of the song When There Are No Strangers to Love?
Hello once more. Linus,
You need to say it
how can I assist you today?
way quicker. Hey Siri, what's the hook of the song Where There Are No Strangers to Love?
Oh, hey there. Linus, how can I help you today?
as useless as ever.
Yeah.
Let's blame it on the shitty internet here.
So it's slightly broken still, but...
You do the backup.
Oh, I can actually do the backup, yeah.
We have backup.
Let's do that.
Oh, this is the wrong one. This is the wrong one.
This is the wrong...
This is the one with less AI and we want more AI.
We want more AI. Right.
What?
The hook of the song where there are no strangers to love.
One sec. Oh, we're going straight into a Rickroll, aren't we, Linus? Well, the hook of Never Gonna Give You Up by Rick Astley goes like this: never gonna give you up. Never gonna let you down. Never gonna run around and desert you. Classic 80s goodness right there. Great choice.
Still have a couple of things. For example, we have Mixed By. Now, the thing is, the HomePod actually has a microphone in it, obviously, because otherwise we couldn't talk to Siri. The thing is, we can use that microphone as a bug. And the good thing is, for an attacker, that there's no microphone indicator, so you could spy on someone without their knowledge. And, what you can do is you can just directly stream audio data via TCP or UDP to another server. And for this demo, we would like to thank Elias Lamnios, simply because he actually helped us do that stuff. We had a few problems with that. Yeah, there was stuff like it just would not record anything or would hang, and help us fix that.
He did a bunch of tweaks related to audio, so I just asked him, hey, can you do that? And then he just figured out all the low-level APIs we need to call to actually get to the mic on the HomePod. So thank you.
And we can actually show a demo of that. Der Vorforward ist da. Clearly not compiled.
We need to compile it first.
We are very well prepared.
So actually the reason why we're it seems like we're not very prepared, but we actually are. So what we also show in a bit is a couple days ago, Apple released iOS 17. So we spent 2 days waiting for the update to download. We restored the HomePod to tvOS 17, and then we actually doing this live demo jailbreak on the HomePod running the latest version of tvOS 17.
Yes.
So basically. So here's the mic, and it goes to the computer.
Okay. Yeah, let's talk about a few implications of that. Now, the thing is, there's no easy way to detect if a HomePod has been jailbroken. The reason is we don't do any persistent file system modifications. Like the next time we start the HomePod, everything will be gone and no one will really be able to find anything anymore in there. So there are no indicators of compromise. And another problem is there's no way to run your own code on the HomePod without jailbreaking it, which means that assuming someone else jailbroke your HomePod, you cannot just run your own code to try to detect it. especially because in order to jailbreak it yourself, you have to reboot the device. And yeah, that's kind of a problem. And
so if you never unplug your HomePod, it just stays there forever and you don't know it's there. So make sure to unplug it every day.
Yeah, that's it. So it's the HomePod only reboots when it's updated normally. So yeah, you can stay jailbroken for a long time. The thing is, it takes about 5 minutes to open up a HomePod and jailbreak it. So assuming you have an evil mate, then maybe you should be a bit careful. And yeah, without the microphone indicator, someone could easily spy on you without you actually noticing this. So everyone get paranoid now, I guess. Or maybe not.
One more thing.
Yeah, we actually have one more thing.
So we presented connecting the HomePod to ChatGPT to add more AI, unless you don't have enough AI with the stock Siri. But what if you're like, hey, I want to have less AI? So what's happening here is I'm listening in with the MixPy onto Linus's HomePod, and then I just
Hello, Siri.
serve the requests manually.
Good afternoon, Master Linus.
Well, how are my finances?
Let me check. Your bank account is doing very well, Master Linus.
Linus cannot see my screen. Just the HomePod.
That's perfect. Is there anything interesting in the news?
One moment. People are asking what the best iPhone jailbreak is.
So when we recorded that, this was actually on the front page.
That's obviously Fugu. Tell them that.
Yes, Master. Anything else I can assist you with?
Actually, do you have any recommendations on what talk I should watch?
Let me check. The next talk in the iOS and macOS track will be Deconstructing the Beast, a deep dive into JIT compilation attacks in iOS by Shubham Sharma. Maybe you will like that.
Interesting. Thank you, Siri.
It is my pleasure to serve you, Master Linus.
So yeah, that's it for the demos. And question is now, did you like more AI better than less AI or the other way around? Anyway, that's it.
Come to me later if you want one of these 3D printed adapters. Thank you.